Yes, the green wire, also known as the ground wire, should also be sized according to the voltage drop. Although the green wire does not carry current under normal conditions, it plays a crucial role in ensuring electrical safety and preventing potential hazards. In the event of a ground fault, the green wire provides a low resistance path for fault current to return to the source, tripping the circuit breaker or fuse and interrupting the circuit. The green wire grounds the equipment enclosure and prevents it from becoming energized, reducing the risk of electrical shock to users. While the green wire does not typically carry significant load current, it is still subject to voltage drop due to its resistance. Excessive voltage drop on the green wire can compromise its ability to perform its safety functions effectively. Sizing guidelines for the green wire are as follows. Firstly, use the same wire gauge as the circuit conductors or one size smaller. For example, for a 12 American wire gauge circuit, use a 12 American wire gauge or 14 American wire gauge green wire. Secondly, ensure the green wire has sufficient ampacity to handle fault currents. Refer to the National Electrical Code, or NEC, or local electrical regulations for specific requirements. Thirdly, consider the length of the wire run and adjust the gauge accordingly to minimize voltage drop. By sizing the green wire according to the voltage drop, you ensure that it can fulfill its safety functions reliably and prevent potential electrical hazards. The purpose of the grounding conductor is to provide a low impedance path for fault current to return to the source. This is crucial for the operation of overcurrent protective devices like circuit breakers and fuses. If the grounding conductor is undersized, it can impede the flow of fault current, potentially delaying the tripping of the overcurrent device and increasing the risk of electrical shock or fire. The National Electrical Code provides specific tables and guidelines for sizing grounding conductors based on the size of the ungrounded conductors in the circuit. These tables take into account the potential fault current levels and ensure that the grounding conductor is adequately sized to handle those currents. Voltage drop is a significant factor in determining the appropriate size of conductors for any electrical circuit, including the grounding conductor. Excessive voltage drop can lead to inefficient operation of equipment, overheating of conductors, and increased energy consumption. While the grounding conductor does not normally carry current, it must be sized to handle potential fault currents without excessive voltage drop. The NEC provides guidelines for calculating voltage drop in electrical circuits, including grounding conductors. These calculations take into account the length of the conductor, the current flowing through it, and the conductor's resistance. To minimize voltage drop, it is often necessary to increase the size of the grounding conductor beyond the minimum required by the NEC. This is particularly important for long circuit runs or circuits with high fault current potential. There are several methods for sizing the grounding conductor to minimize voltage drop. One common approach is to use the same size conductor as the ungrounded conductors in the circuit. This ensures that the grounding conductor has sufficient ampacity and low enough resistance to handle fault currents without excessive voltage drop. Another method is to use a grounding conductor that is one size larger than the minimum required by the NEC. This provides an additional margin of safety and helps to minimize voltage drop. It is also important to consider the type of conductor used for grounding. Copper conductors have lower resistance than aluminum conductors, so they are generally preferred for grounding applications. However, aluminum conductors can be used if they are properly sized and installed. When sizing the grounding conductor, it is also important to consider the type of equipment being grounded. Some equipment, such as sensitive electronic devices, may require a dedicated grounding conductor to minimize electrical noise and interference. In these cases, it may be necessary to use a larger grounding conductor or a separate isolated grounding conductor. It is essential to consult the NEC and local electrical codes for specific requirements related to grounding conductors. These codes provide detailed guidance on sizing, installation, and other aspects of grounding to ensure electrical safety. Ignoring these codes can result in serious electrical hazards, including shock, fire, and equipment damage. Regular inspections and maintenance of grounding systems are also crucial for ensuring their continued effectiveness. Grounding conductors should be inspected periodically for corrosion, damage, and loose connections. Any problems should be addressed promptly to maintain the integrity of the grounding system. In addition to sizing and installation, proper bonding of electrical equipment is also important for minimizing voltage drop and ensuring electrical safety. Bonding involves connecting all metal parts of an electrical system together to create a low impedance path for fault current. This helps to prevent voltage differences between different parts of the system, which can cause electrical shock. The NEC provides detailed requirements for bonding electrical equipment, including grounding electrodes, enclosures, and raceways. These requirements must be followed carefully to ensure that the bonding system is effective. Another important consideration is the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electrical shock by detecting small imbalances in current flow and interrupting the circuit. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas where there is a high risk of electrical shock. When using GFCIs, it is important to ensure that the grounding system is properly installed and maintained. GFCIs rely on a properly grounded system to function correctly. If the grounding system is faulty, the GFCI may not trip, increasing the risk of electrical shock. Surge protection is another important aspect of electrical safety. Surges are sudden increases in voltage that can damage electronic equipment. Surge protective devices, or SPDs, are designed to protect equipment from surges by diverting excess voltage to ground. SPD should be installed at the service entrance and at sensitive electronic equipment to provide comprehensive surge protection. When installing SPD, it is important to ensure that they are properly grounded. SPD rely on a properly grounded system to function correctly. If the grounding system is faulty, the SPD may not protect equipment from surges. In summary, sizing the grounding conductor according to voltage drop is essential for electrical safety. A properly sized grounding conductor provides a low impedance path for fault current, minimizes voltage drop, and helps to protect people and equipment from electrical hazards. It is important to consult the NEC and local electrical codes for specific requirements related to grounding conductors and to ensure that the grounding system is properly installed and maintained. Remember to always prioritize electrical safety when working with electrical systems. If you are not qualified to perform electrical work, consult a licensed electrician. Improper electrical work can be dangerous and can result in serious injury or death. Grounding is a critical aspect of electrical system design and installation. It's not just about connecting a wire to the earth. It's about creating a safe and effective path for fault currents to flow back to the source, thereby tripping over current protection devices and minimizing the risk of electrical shock. The NEC provides detailed guidelines for grounding and bonding, and it's crucial to understand these requirements to ensure a safe installation. Sizing the grounding conductor involves several considerations. The primary factor is the size of the ungrounded conductors in the circuit. The NEC provides tables that specify the minimum size of the grounding conductor based on the size of the ungrounded conductors. However, there are situations where the grounding conductor needs to be larger than the minimum size specified in the table. One such situation is when the circuit is subject to high fault currents. In these cases, the grounding conductor must be sized to handle the available fault current without excessive voltage drop. Voltage drop in the grounding conductor can have several negative consequences. Firstly, it can reduce the effectiveness of the overcurrent protection devices. If the voltage drop is too high, the fault current may not be sufficient to trip the breaker or fuse quickly enough to prevent damage or injury. Secondly, voltage drop can increase the risk of electrical shock. If the voltage drop is high, the voltage on the grounded parts of the equipment may rise to a dangerous level, creating a shock hazard. To minimize voltage drop in the grounding conductor, it's often necessary to increase the size of the conductor. The amount of increase depends on the length of the circuit, the amount of fault current, and the desired voltage drop. There are several methods for calculating voltage drop in the grounding conductor. One method is to use the voltage drop formula, which takes into account the length of the conductor, the current flowing through it, and the conductor's resistance. Another method is to use a voltage drop calculator, which is available online or in electrical engineering software. In addition to sizing the grounding conductor, it's also important to ensure that it is properly installed. The grounding conductor must be connected to the grounding electrode system in accordance with the NEC requirements. The connections must be tight and corrosion resistant to ensure a reliable ground path. Bonding is another critical aspect of grounding. Bonding involves connecting all metal parts of the electrical system together to create a low impedance path for fault current. This helps to prevent voltage differences between different parts of the system and minimizes the risk of electrical shock. The NEC provides detailed requirements for bonding electrical equipment. These requirements specify the types of bonding jumpers that must be used, the locations where bonding jumpers must be installed, and the methods for making bonding connections. Brand fault circuit interrupters, or GFCIs, are another important safety device that is used to protect people from electrical shock. GFCIs work by monitoring the current flowing in the circuit and detecting any imbalances between the hot and neutral conductors. If an imbalance is detected, the GFCI will trip the circuit, interrupting the flow of current and preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Surge protective devices, or SPDs, are used to protect electronic equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. SPD work by diverting the excess voltage to ground, protecting the equipment from damage. SPD are available in a variety of types and sizes. The type of SPD that is needed depends on the type of equipment being protected and the level of surge protection that is required. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. The grounding conductors should be inspected for corrosion, damage, and loose connections. The connections should be tightened and repaired as needed. The grounding electrodes should also be inspected to ensure that they are still in good condition. If the electrodes are corroded or damaged, they should be replaced. In addition to the NEC requirements, there may be local electrical codes that apply to grounding and bonding. It's important to check with the local electrical inspector to determine if there are any additional requirements. Electrical safety is paramount. Always follow safe work practices when working with electrical systems. Wear appropriate personal protective equipment, such as gloves and safety glasses. To energize the circuit before working on it. Use properly insulated tools. If you are not qualified to perform electrical work, hire a licensed electrician.